It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to lesson 16 here, where we're going to talk about the remainder theorem, which yes, has to deal with remainders that we learned about in the previous lesson. So consider the polynomial here, divide f of x by x minus 2. So take a minute and divide f of x by x minus 2. All right, hopefully you paused it. X minus 2, I'm dividing 3x squared, 8x, and negative 4. So I need a 3x up there, negative 6x there when I multiply. I'm at negative 6. What minus 6 is 8? Well, 14 minus 6 is 8. So I need a plus 14 minus 28. Well, what's my remainder? 28 plus my remainder has to give me negative 4. Negative 28 plus my remainder, so I'm going to add 28 to both sides, which gives me a remainder of 24. So my answer is 3x plus 14 plus 24 out of x minus 2. Then I ask you to find f of 2, which means go to f of x here and replace every x with a 2, right? F of 2. When I plug in a 2, what does it spit out? Well, I can just type this whole thing into a calculator right now if I had one near me. I wish I did. 412 plus 16 minus 4 gives me 24. So f of 2 is 24. That when x is 2, y is 24. All right, let's try this one here. Divide by x plus 1. So I'm dividing by x plus 1 of x to the third minus 3x squared, 6x, and 8. So I get x to the third, which gives me an x squared up top. I'm at positive 1. How do I get to negative 3? I'm at positive 1. I got to go down 4 floors of stairs. Negative 4 and 1 make negative 3. Then we start again. Negative 4x, negative 4x times 1. Got to go up 10 floors there. 10 minus 4 is 6. And then finally 10. That leaves me with a remainder of, how do I get from 10 to 8? A remainder of negative 2. So the quotient is x squared minus 4x plus 10 plus negative 2 over x plus 1. Remember, it's quotient, plus you have a little fractional piece left over because it didn't divide in nicely, so negative 2 over x plus 1. Find g of negative 1. So g of negative 1. Negative 1 cubed minus 3 times negative 1 squared plus 6 times negative 1 plus 8. So I get negative 1. Remember, I don't have a calculator, so you could have just done this all on a calculator. Negative 10 plus 8 is negative 2. Something is going on here. Something is going on here. Maybe we'll find it out. Maybe something different will happen this time. Maybe something different will happen this time. Divide by x minus 3. So I got x to the third. Warning. 0x squareds, 2 x's, and then a negative 3. All right, here we go. X squared, negative 3x squared. But I want 0. So once you get good at this reverse tabular method, you'll see that you can kind of speed through these problems. Plus 3x, which makes negative 9x there, but I need 2 of them. So if I'm at negative 9, how do I climb up to 2? Well, I have to go up 11. I'm at negative 33. I need to climb up to negative 3, so that's a remainder of 30. I need to go add on 30 there to get to 3. So I have a remainder of 30. So x squared plus 3x plus 11 plus remainder over divisor. 30 is my remainder. I'm dividing by x minus 3. H of 3, that means take a 3 and plug it in. 3 cubed plus 2 times 3 minus 3. Well, hopefully by now you know that 3 cubed is 27. And what do you know? I get 30. Now, something strange happened every single time. When I divided by x minus 2, I had a remainder of 24. When I plugged in a positive 2, it equaled 24. When I divided by x plus 1, I got a remainder of negative 2. When I plugged in a negative 1, not x plus 1, when I plugged in a negative 1, I got negative 2. When I divided by x minus 3, I got a remainder of 30. So when I plug in a positive 3, I got a value of 30. So this here is called the remainder theorem, and it's a really powerful tool that allows us to check our work and gives us some interesting facts about polynomials. So the remainder theorem states if p of x is a polynomial, then when p of x, sorry, restart. I'm going to say let p of x be a polynomial. Let p of x be a polynomial, period. That's a sentence. If we divide p of x, by x minus a, the remainder will be p of a. So what does this mean? If I have a polynomial here that I'm dividing by x minus a, I'm dividing it by something, the remainder, that ratio there, that quotient, has a remainder of p of a. Take the opposite thing of the divisor, the opposite value of the divisor, this 0, right? If I have a factor of x minus a, I have a 0 of a. Plug in that opposite value into the function, and that actually equals the remainder. That actually equals the remainder. So determine if x, so we actually get a follow-up to the remainder theorem. We actually get a very important corollary to the remainder theorem, which is this. If p of a equals 0, then x minus a is a factor. This is a huge result of the remainder theorem. If I have a remainder of 0, then I am a factor. So if p of a equals 0 is saying if I have a remainder of 0, and you always have a remainder, you just have a remainder of 0, then x minus a is a factor. So determine if x minus 4 is a factor. So I could determine if it's a factor by 1 dividing, which we can all do. Let me just squiggle here to get rid of half the page. I could divide by x minus 4. All right. This is very tedious because I don't actually care what the quotient is. I just want to know, is it actually a factor? Does it divide in nicely? So 2x to the third, 2x squared, negative 8x squared. Well, I need to add on 3. I need to, negative 12, I need a positive 1x, 1 minus good. So notice, what's my remainder? I have negative 4 and I want negative 4. My remainder is 0. So x minus 4 is a factor. Why is it a factor? X minus 4 is a factor because we get a remainder of 0. These two multiplied together gives me that cubic polynomial. Here's the fast way of doing it. The fast way of doing it is the remainder theorem. Instead of doing all that division, if I want to know about x minus 4, that means I'm plugging in positive 4. Plug x equals 4 in. I want to know about x minus 4, so I'm plugging in a 4. So f of 4 equals 2 times 4 cubed minus 5 times 4 squared minus 11 times 4 minus 4. And then at this point, you just type all of this into a calculator. Which I don't have on me right now, so I'm faking it. I'm doing all of this mental math. But again, at this point, you can skip all these steps and just type it into a calculator. It's minus 128. We get 0. So f of 4 equals 0. So what this tells me, this number that I just found right here is the remainder. I didn't have to go through and do all that division. I could have just plugged a number in, and I get the remainder. So we can say x minus 4 is a factor since f of 4 equals 0. This tells us the remainder would be 0. Tells us the remainder would be 0. Okay, so there's two ways you can determine if something is a factor, which is going to be really important because then we can keep on factoring. If I can divide out a factor, that means later on I can keep on dividing. So we're only a factor if you have a remainder of 0. You're going to be hearing me say this a whole lot. I'm only a factor if my remainder is 0. Determine if x plus 2 is a factor. So let's just use the remainder theorem here. So if I want to know about x plus 2, that means I need to plug in x equals negative 2. I plug in the related 0. I plug in the opposite value. So p of negative 2, I'm plugging in a negative 2. Everywhere I see an x is becoming a negative 2. Negative 8 plus 4 plus 54 minus 15. That gives me 58 minus 23. 58 minus 23 is 35. So what this tells me, if I divide p of x by x plus 2, the remainder will be 35. I just found the remainder. The remainder will be 35. Is that what I want? Is x plus 2 a factor then? No. X plus 2 is not a factor because the remainder is not 0. To be a factor, you have to have a remainder of 0. That's the only way for something to be a factor of a polynomial, is for the remainder to be 0. Consider this polynomial here. So again, big idea. How do I check for something being a factor? I want the remainder to be 0. And I don't need to divide. I can just plug in the opposite number to make sure that happens. Consider the polynomial, find the value of k so that x plus 1 is a factor. If x plus 1 is a factor, that means it divides in. That means it divides in. So how do I check if it's a factor? Well, that means x equals negative 1 is a 0. So when I plug in negative 1, it should equal 0. If I want that to be a factor, everywhere I see an x, I'm going to plug in a negative 1 and set it equal to 0. If I want to know about x plus 1, I'm plugging in a negative 1 and setting it equal to 0. So negative 1 plus k minus 1 plus 6. Negative 1, and 6 is positive 4. So k equals negative 4. How do I make this polynomial have x plus 1 as a factor? You let k equal negative 4. So p of x would equal x to the third minus 4x squared plus x plus 6. That's how I get negative x plus 1 to be a factor. To be a factor, negative 1, the opposite has to be a 0. So that's how I get that started there. Two more and we'll be done with this whole remainder theorem nonsense. So find g of negative 1. Well, how do I find g of negative 1? I plug it in. 2 times negative 1 cubed minus 3 times negative 1 squared minus 17 times negative 1 minus 12. And at this point, you just type that all into a calculator. And hopefully it equals what number? If I want it to be a factor, hopefully it equals 0. But I don't have a calculator with me right now. Even though I'm in my classroom, I still don't have a calculator. Negative 5 and negative 12 is negative 17, so it does equal 0. When I plug in a negative 1, it equals 0. So since g of negative 1 equals 0, the remainder, when I divide, when g of x is divided by x plus 1, is 0. Therefore, x plus 1 is a factor. How do I become a factor? I'm a factor if the remainder is equal to 0. In this case, it was. How do I tell if something's a factor? There needs to be a remainder of 0. So here's p of x. Find the remainder when p of x is divided by x minus 1. Well, if I'm dividing by x minus 1, I plug in the opposite. That means we're plugging in x equals positive 1. So I go to positive 1, and there it is. What's my y value? P of 1 equals 4. Now, whatever it equals there is the remainder. So in this case, it's 4. The remainder is 4. X minus 1 is not a factor. X minus 1 is not a factor because the remainder is 4. Okay, so it's weird to see it from a graph form, but the remainders are really just the y values. The y values of either a table or a graph are the remainders. So if I want to know about x minus 1, you plug in a positive 1. If I want to know about x plus 7, you look at negative 7. So hopefully this makes sense, and we'll be definitely practicing it as the days come on. And I'll see you guys soon as we almost finish up Unit 1.